Hi, everybody. So Ken's talk was a really good lead-in to what I'm going to present to you, because this is the results of a effort under an allocation from the Great Lakes Consortium, and it's all about finding productive ways to scale up and to allow more scientists to compute at blue water scale and beyond. So the work that I'm going to talk about is basically taking about a decades of work in workflow systems, starting for grid systems, then moving on to cloud and multi-cluster kinds of situations, and then scaling this up to extreme scale machines. So it's the work of Scott Creeder and Timothy Armstrong, and also Justin Wozniak were the key people who actually implemented a lot of the things we'll talk about here. So the applications that we're talking about here are trying to find a programming model that'll help people program the outer loops of extreme scale applications, especially things that involve nested types of iteration with highly dynamic runtimes, data flow needs internally to literally form a workflow on an exascale machine. So the example shown here is simply drug discovery, but it also typifies material science and materials by design applications. In this case, we're illustrating an example where you have a small number of proteins and a very large number of chemical compounds, and you're trying to dock those ligands into proteins, reducing a very large search space to something more affordable than running that through very fine-grained molecular dynamics and finally selecting targets to take to crystallography in the APS or other kinds of wet lab kinds of settings. So it's basically situations where you have an explosion of cases to explore highly dynamic situations, and then essentially a workflow pattern that you want to program on a very large scale machine. And what we're going to talk about is a programming model that is manifested in the Swift parallel scripting language, and how this language has evolved from basically running applications on clusters to running functions, workflows consisting of in-memory functions and in-memory data passing, and then finally the extension of that to a hybrid environment where we can not only take advantage of a vast number of cores, but also do many task programming on individual GPUs. So what we're trying to give to the scientific programmer is a very simple, high-level way to describe the outer loops of complex applications. And we call this programming model implicitly-parallel functional data flow. In other words, the user writes ordinary, what looks like sequential code. The runtime system and the compiler work together to exploit vast number of cores from that sequential code. And so in these kinds of applications, parallelism is pervasive throughout your program. So for example, these nested for loops are all done fully in parallel with essentially the entire call graph of a high-level program expanded the instant the program starts, and then tasks dynamically distributed out to machines at runtime through very efficient means. So in a simple example of what we mean by implicitly parallel is that in this block of assignment statements, the two functions f and g run in parallel without any directives by the programmer. In other words, the system knows from data flow that there's no dependencies and that they only have to block when it computes the sum of what those two functions returned. And that simple model is extended all the way through the call graph, through nested loops, across function calls that'll be passing arrays and structures and things like this. So very, very simple model, but very powerful runtime. And the challenge we're facing is how to scale this up to, literally to the million core level. So this is just another illustration of how this works at runtime. And the other word I used in describing this paradigm is functional. So from the functional programming model, we take this idea of write once variables, and this both imparts a simplicity to workflow procedure design, but it also is the magic that enables the runtime to do this highly automatic parallelization of your code. So Swift, when we created it, it was really targeted at this kind of grid model, and it was also targeted at running application programs, entire application codes, both serial and parallel based on MPI or OpenMP or any other parallel model. But we treated those codes as the leaf functions of our applications and ran them across a fairly wide variety of machines, from a multi-core desktop all the way up to, at the time, the largest supercomputers. But then we hit a bottleneck. So the original Swift that we developed was interpreted from a single, it was a Java application, and it's still our mainstream, classic implementation in use today, but it's a single node-based Java application. And it's limited to pumping out about 500 application invocation calls per second. So that was at the time a very large number. Systems that were running batch scheduling were really struggling to do, a few tasks per second overall on a large machine. This implementation was getting about 500 per second, but it would still, when we were trying to fill our 18,000 core Cray at UChicago with 500 tasks per second, that's only feasible at a task duration, on the order of 3 to 5 minutes or so. So that kind of limits, that's a pretty fine-grained task for a workflow system, but certainly not, petascale levels. So what we wanted to move from was this notion of a single node interpreting the program to being able to treat the interpreter itself as a large-scale parallel program. And that was done under the DOE Xstack program. So we spent the last 3 years going from what was 500 tasks per second, and we set a goal of getting to 1 million tasks per second by distributing the evaluation of this data flow programming model over lots of nodes. And so this was done under a program called Extremescale Many-Task Computing under Xstack. And we came up with an architecture like this, where the evaluation of the program was broken up by the compiler into a set of rules, and then distributed rule engines spread throughout many nodes of a large-scale machine would collectively interpret a program. So as you look at the call graph of a workflow-like data flow program, as soon as that program starts out and it starts emitting for loops, and the for loops start emitting tasks, those operations are broken up and spread out throughout many, many rule interpretation engines. And you can set the number of rule engines and then the number of load balancing nodes that are going to distribute tasks to a level that is appropriate for the topology of the program you're running. And the typical rule of thumb would be, less than 10% of the resources would be used for actually doing the interpretation of the data flow program. Most of the resources would be actually running, application leaf tasks. So then we teamed up with Ioan Raicu's team and his student Scott Creeder at IIT, who were exploring the concept of many-task computing, which is basically the underlying model of what's behind this Swift data flow model. And they were asking the question now, could we take this idea of many-task and put it on an accelerator? In other words, can we take an accelerator and use an accelerator itself as if it was a little cluster? And so out of that came the first generation of this, of a software implementation to do this, and it was called GeMTC, for GPU-enabled many-tasking. And it has an architecture that's really not that dissimilar from the kinds of things that Swift was doing at a cluster level, and then we basically integrated these two software bodies together. So now we have Swift on a machine that's now capable of treating a GPU almost as if a GPU was a computing site. And with the current CUDA-based implementation of GeMTC, we can now many-task a GPU like the K20Xs on Blue Waters down to the level of 1 task per warp. So effectively that means we can put 168 independent tasks, each one getting 1 warp of 16 microcores on the GPU working on independent tasks. And so a lot of this research to date has been focused on, can this be done? There's a lot of questions now that we're facing in terms of what applications and what application instruction mixes are really amenable to high speed up with this kind of independence. So there's a paper that is just published, or will be just published, for HPDC 14 that shows the preliminary study, which is almost entirely CUDA and NVIDIA based, with a tiny bit of results of applying the same paradigm to the Intel Phi. So here's the API, basically, and the implementation of this is actually very straightforward. There's a lot of sort of low-level programming work involved in getting this mechanism to be faster and faster, but we're taking the same trajectory we took with core Swift, going from a 500 tasks per second level out to extreme scales, and the same kind of basic software engineering techniques are working for getting this API to the same level of performance. So the way this works is basically now in Swift, with the work we did under the EXM project, I mentioned that we are able to take a in-memory function and treat that as one of our leaf functions in the program graph instead of just any application program. So for getting onto the GPU, basically, you take the same approach. You take the core of your application, create essentially a microkernel that talks the GeMTC API and link that in. And that essentially makes what's running on the GPU independently callable, from the same kind of high-level Swift code that I showed you earlier with, for example, the nested for loops. So now when these things are put together, this is the topology we've been testing on Blue Waters, where we take one server per Blue Waters node. And so basically one core of each node, one CPU core, serves both load balancing and Swift rule interpretation. The remaining cores can serve as CPU workers, except for one core, which actually acts as the interface and runs the client API to send tasks down to the GPU. So it's basically 14 cores for actually doing CPU work, one for load balancing and interpretation, one for GPU liaison. So a few results that I unfortunately can't speak to extremely authoritatively, but these are taken from the HPDC paper that was led by Ioan's student Scott. So this is first showing, so the application we tried here was a very lightweight proxy code for molecular dynamics. And it shows very, very good scale up to about 90% efficiency on, I think this is for 8 nodes. So it's 8 nodes times 168 independent tasks per node. The ability to get to a very high task rate, so reaching 2,500 tasks per second on a single K20X. So this is also a measure of independent multitaskability of the GPU. Now here we're seeing connecting Swift, or driving the GeMTC GPU-based interface through Swift at a level of about, I think this is about 60 or so nodes at a level of 10,000 independent tasks. And this is reaching a performance level of about 70% efficiency. Now here we're starting to stress the system in kind of an extreme scale. We sort of came from a world where where running like a 60-second task was like a big deal in the grid world, and now we're trying to bring that down to like sub-second tasks down to 25 milliseconds. So at 25 milliseconds, we're really painfully stressing our system, but even at a quarter of a second task, we're doing pretty good at 90% efficiency, running at 512 nodes and a parallelism of about 86,000 independent tasks. So I'm going to sort of skip through these because I want to bring you to another, the work that we did under this GLCPC effort really focused on two things. It focused on, can we multitask the GPU in the manner I just described, and can we get Swift to scale to the hundreds of thousands of core range with sub-second tasks. Okay, so this is a result that we're really excited about core Swift. So this is without a GPU, and it's basically just measuring how fast can those Swift for each loops distribute tasks on this new many-task architecture. So this is where we set ourselves a goal of getting to 1 million tasks per second and running on 500, so this is about 2/3 of Blue Waters, using integer cores, so 32 cores active per node, and we're getting to a task rate here of about 1.5 billion tasks per second. So we went in about 3 years of development from 500 tasks per second to 1.5 billion using the same programming model. So that's a result that we're extremely excited about. And a paper that has been submitted to SC, which is available at a link that's in the presentation, it was on the slide that had the picture of Mira and Blue Waters, has results for about 6 different applications. So this was an application of nested for loops, a tree reduction program, unbalanced tree searching, a wavefront-like many-task application. And this actually is an interesting application. This is basically a simulated annealing optimization of graph studies of scientific citation analysis and basically a sociological study of the propagation of scientific knowledge. So this is going beyond getting economists to be able to program petascale machines, but it's allowing sociologists to do that same kind of thing. So I think I'm going to close here and just take any questions. And one of the things I'd just like to say is that we're very eager to find users. So we've got users across virtually every domain of physical science and growing into the social sciences. And we're very eager to work with you if you have an application that you think would be productively enhanced with this kind of programming model.
Okay, thank you.
Thank you all.